Okay. Is anyone interested in supporting girls in STEM?
Yes.
So there's Girls Fest that's happening here on campus. We're getting flooded with 300 to 400 Girl Scouts from across the state, even beyond. They're coming here for a STEM, what's that?
I'll buy that.
Just come camp out. So we're looking for volunteers for the STEM Fest, both to help with the activities on the Saturday. This is November 3rd, Saturday, November 3rd. Some of the girls are actually camping out on campus the night before. Like, I think in Dickinson Hall, they're like getting cots or the sleeping bags or whatever it is. But the real thing that we need help with is like setting up and breaking down and then possibly running some of the events with others. So there's chemistry events, there's environment, like sustainability events, there's natural sciences, and a few other things. So if you're interested and you're available on November 3rd, send me an email and I'll put you in touch with the right people and we'll see if that can help. For the event running itself, we are trying to do it as all women so that the girls can see women in STEM. But as far as the support for doing other things, we need help of all genders. So that would be fantastic. So just let me know if that's something that interests you. We would be happy.
There's no bonus added to that, is there, if we help?
What's that?
There's no bonus if we help, is there?
There is praise from individuals who are very happy to have you help them.
What if like a one-point bonus, like 10 points?
Not enough.
If it was something I could do evenly to everybody, and if it wasn't just like a one-time event, if it was like do one thing throughout the semester and this would be one of them, then I'd be game for that. But just doing a one-time event is.
We got plenty of
Okay, one-time event.
All right. So you guys have been working on naming in your homework, and we're going to talk a little bit about it in class and kind of start building off of that. So has everyone got a chance to click in the name for this compound? Okay, I'm going to give you 30 more seconds to finish, figure out what the name is, and click it in. Yeah. What is the robotics name? Yeah. Around. She's interested. She is. Okay. We have 44 responses. How do we go about determining the name of this? I'm going to write down a name, and I'm going to see if you guys think this is a great name. What is the name of this over here? Acetate. All right. Do we always see it as CH3CO2? No. What do we sometimes see it listed as? Okay, so it can either be CH3COO or it can be C2H3O2. All right, so it's just saying that instead of showing you what the formula is, it just gives you how many of each atom. So both of those are acetate. So let's do, is this the right name? Magnesium diacetate. Why? Can I have a hand raised? And we're going to try to hear from a lot of people again today. Hand raised. Why is it? Kayla.
That's what you prefixes with non-metals.
Great. So we do prefixes with non-metals to say how many of them there are. Why do we not need it for this? Crush.
It's because it's 2 ions.
Okay, so it's 2 ions, that's right. To be more specific, why does the fact that it's 2 ions mean that we don't have to do this? Aaron? Great. When we find magnesium as an ion, it will always have the same charge. What charge does it have? I like how people just repeat what you say. Love says it with such confidence. Minus. So magnesium is always going to be +2. And then acetate is always going to be? So there's only one possible combination we can have with these, and it is 1 magnesium with 2 acetates. That's the only way we can get a neutral salt, by making a salt with those 2 ions. If we have a cation that is not always the same charge. How do we deal with that? I'm going to have you talk to your neighbor for a minute. Let's say instead we have iron acetate. Talk to your neighbor. How do we name this so that we actually know what that combination is? Because now we don't have magnesium. It's not always +2 for iron. There's a lot of different options. So how do we name that? Please. All right, so in your pairs, how do we name this compound with your discussion you just had? In your pairs, in your groups, talk to the others. How would you name that? All right, new voice. Can I get someone in this back corner of the room?
He just had it. He did.
Jason.
I said Fe with 3, Roman numeral 3 in parentheses, and then the acetate.
Okay, so you said Fe, you're saying the symbol, we're going to say the name, right? So iron, Roman numeral 3, acetate. Why did you give it a Roman numeral 3?
To charge the acetate. So it would be neutral.
Great. So if we were to go in and say, well, we know that acetate is always a -1. So in order for that to be a neutral salt, we have 3 minus, so what's the plus going to be? Plus has to be 3 plus. So it's iron 3 plus, along with 3 acetates -1. That's going to be a neutral salt. And to make sure for any transition metal, and remember transition metal is this solid D block right here in the middle. Almost every single one can have multiple charges. There's a couple exceptions.
Silver, copper, well, not copper, but silver.
This diagonal line right here. Aluminum, zinc, silver. +3, +2, +1. Those 3 are the only, I guess aluminum's technically not I guess it is a transition metal, right? These are still transition metals under this red line.
And cadmium.
So aluminum, zinc, silver are the 3 I want you to remember. 3, 2, 1. Aluminum is +3 is kind of easy to remember because it's in main group 3. So 3, 2, 1. If you ever see those, I don't think you'll ever use a Roman numeral for those because those are the only charges they can take on. Other than that, every single transition metal, we're going to want to write the Roman numeral to represent what charge state we have for the transition metal. Are we going to use Roman numerals for calcium?
No.
What about yttrium? Why? We're going to have to because that's a transition metal. Okay? Then the next question I have for you guys is, I don't know. I don't know why it's grayed out, but that's the second question. Is magnesium acetate soluble? 20 seconds to click in your answer. Couple more seconds. All right. First question. What does soluble mean?
Water.
I love all the hands raised there. Thank you. Okay, so the moan from the audience was it dissolves in water. What we're going to learn in chemistry is that there's a lot of different liquids that exist, or solvents we call them. Just because there's a lot of different ones, we always, in chemistry, unless it's specified, will focus on water. If there's a liquid, it's going to be water for the most part. So if it's soluble, I mean, does it dissolve in water? And That means if we took a salt of magnesium chloride, we had a bottle of it, we poured it into water, what's happening to those ions if it dissolves? I see hands raised from different people. We got a magic school bus. We could go and zoom in and look at what's happening to those magnesium acetate compounds. What happens? John?
They would disassociate in the water.
Great. So we have a negatively charged acetate. We have a positively charged magnesium, 2+, and we have multiple of those kind of together. If it goes into solution and dissolves, that means that those will separate. They don't just separate and float around by themselves, though. They float around kind of covered by a sphere of water. And so water, we're going to talk a little bit more about that when we talk about intermolecular forces, that we have interactions between water and those ions that is more favorable than the ion with the ion. So it's a matter of stability once again. What's more stable? Is having water around those ions or having an ion next to the ion? So that salt, deciding whether it's soluble or not, is saying when we pour it in water, is magnesium going to separate from acetate? And if those things are separate, we dry it up, we can evaporate the water, they'll come back together. Or we can add another salt and see if the new ions are soluble with each other again. So how do we determine whether it is soluble or not? Can someone hold up the answer? All right, Logan, can you turn that around? Has everyone got this and started using it? So that's our solubility table. I sent it out on Monday, but I don't know if people were able to open that. I guess your TAs, your instructors have sent it out as well. So how do we use a solubility table to answer this question? To make sure that we orient ourselves. What are all on the y-axis? What are all these? These are all of our, not polyatomic, because some of them aren't poly, but these are all our negatively charged ions, or anions. And across the top, cations. So if we're talking about magnesium acetate, we're going to go across the table until we find magnesium. It's a terrible color. And then we're going to go down until we hit acetate. And if you notice, this is how acetate is written. It's that crappy way that doesn't actually show anything about the formula. So we're going to go and we're going to figure out where those two intersect. And it's white. What does white tell us? Soluble. Does that mean we can pour an infinite amount into water and it'll keep dissolving?
No.
Okay, so down here at the bottom, you can say that it's above 0.05 molar at room temperature. We haven't really talked about molarity. That's a concentration. So if you have too much of it, too much of anything won't dissolve. You know that for sodium chloride, right? Table salt. If you pour table salt in water, it dissolves, it dissolves, it dissolves. And then you have a big pile of it at the bottom if you keep pouring too much. Called brine at that point.
Will the chart be provided on the test?
The chart will be provided on my tests, except for the ACS test. And maybe on my final, maybe not my final. I haven't decided yet. So there's been a discussion amongst the faculty that teach this course about whether we provide you with a chart or whether we have you memorize it. The arguments for memorizing it is that there's a lot that you come in contact with regularly through medicine and other applications. So you should really know those ones, but you shouldn't know the whole chart. And so I kind of agree with that to some extent. Are there any major trends on here that we can memorize pretty easily?
Yeah, anything from acetate.
Joey? Go ahead.
Anything from acetate up is soluble.
Okay, so up is a little less than clear because we have to remember, so yes, the ones here and above are always soluble, and so we need to know what those ones would be, right? So that's nitrate, perchlorate, chlorate, acetate. No matter what we combine those with, they're always going to dissolve at a concentration of this or lower.
Group 1 atoms are always soluble.
Group 1 is always soluble. So we have sodium, potassium. Does that keep going if we go all the way down? Do we have
Well, yes,
lithium is not on there. Rubidium and cesium are not on here. Yeah. So group 1 metals, if they're ions, we're going to find those as soluble.
What are these stars for?
The stars are interesting. The stars they are soluble, but they're reactive, and so they don't stick around very long.
Oh, so, and ammonium is there. You know, ammonium is always soluble.
Right, so ammonium, as well as the group 1 metals, ammonium is always soluble. So basically what I want you guys to get out of this table is you need to know how to use it. If I give you a random salt that's a combination of these, you need to be able to say whether it's soluble or not. And I want you to try to memorize which ones are always soluble and which ones are pretty much always not soluble. That's going to be kind of useful to think about. I will give you this on the next test, next two tests, exams 2 and 3, there's a good chance I won't give it to you in the final exam. Okay? So keep that in mind. There's not too many to memorize. And if it were only my final exam, I would be fine with you just having this. But because there's a national standardized test, it may be a different job.
Shit, I was going to argue against the people that say you should memorize it. My wife's a physician. She looks at stuff all the time.
True. But there's always something to do with... So you could say that about all knowledge to some extent. And we do need to have some knowledge in order to have quicker, facilitated conversations. So if you're going to inject the patient with something that is...
You should look first.
Good to look first and to know that there are some that are soluble and some that are insoluble. All right. Markeith, Mohammed, please get your clickers registered. You just got the two of you. All right. So talk to me after class if you want to figure out how to do that. All right. So you guys are using this table in lab this week and next week. And I want you thinking about the molecular level. I want you thinking about what those ions are, what they look like, and how they're interacting with each other. Have you guys started drawing all of the polyatomic ions yet? Blue structures for them? No. All right, so every time I show you a polyatomic ion, always think about what would that Lewis structure look like, how would I draw that? So our learning objectives for today, we're going to be talking some more about using molecular formulas and specifically larger structures. If you guys look at the worksheet that you have today, there are a lot of very large structures. So what I want you to be able to do, I can basically tell you what exam 2 is going to be. I'm going to give you some pharmaceutical drug, like the ones that are listed here. You're going to have to tell me a ton of information about it. So the worksheet from last class has some of those statements and the things you're going to need to do on it. So make sure to kind of be able to look at a molecule, work through different parts of it. What does this mean? What does the structure tell us? Those kinds of things. So we're going to talk about determining steric number, AXE group for any atom. We can kind of point at any atom and say what that is. Predict electron pair geometry, molecular shape. And then based on the polarity of the bonds, we should be able to say something about solubility. And we'll talk more about that today. So let's take a look at Abilify, which is our first drug on the front page. Around the atom that I have pointed at, what is the molecular shape? And you may want to think about a couple of questions before that that lead into what that is. Do another 20 seconds. Our next test is a week and a half. 8. What's that?
I said, do you like Star Wars?
All right. I think everyone has clicked in. So we don't have a very strong consensus. We actually have a very large number of different responses. Turn and convince your neighbor that you are right. If you agree with your neighbor, turn and talk to someone else. Try to find someone with a different opinion than you and figure out why they answered the way they did and convince them that you're right.
I've never seen it. I've never really read these kinds of things.
Alright, click in your thoughts. You can resubmit the same answer, you can submit a different answer if you change your mind. The clickers are open. A couple more seconds. Alright, did anyone change their mind? And maybe we can hear why. Manu, can you share your thoughts? You got called out. Or you have a good explanation? Is that why Kiana's pointing you?
No.
Can you share your thoughts on how you solve this problem or what you're thinking?
I just guess. I put trigonal planar because see 3 elements. It's 120 degrees.
Okay, so it looks like it's about 120. You say you see 3 elements around that?
Yeah.
What are the 3?
Nitrogen and ketones.
Say again, this carbon up here? We talking about the same carbon?
He's thinking the whole structure is one carbon.
Ah, so this, remember where a line starts, stops, or changes directions is a carbon. So how many carbons do we have in this ring?
6.
There's 6 carbons in this ring. This one we're pointing at, how many bonds are shown to that carbon?
3.
2 bonds on the left side, 1 bond on the bottom.
But there's another hydrogen bond. There's a hydrogen bonded.
So Gail, can you describe?
Well, the way I thought it was that there's no bond to a carbon, and then there's a bond to a chloride, and then what the arrow is.
Bond to a what?
The chloride?
Nope. This is another carbon here at the bottom. So that's a chlorine attached to this carbon. We're talking about this carbon where the arrow is.
There's so it's bonded, no bonded to a carbon, then on the bottom to another carbon, and on top to a hydrogen.
So remember we said last class, every carbon will have 4 bonds in this class. So if you don't see 4 bonds, what's implied? At least 1 hydrogen, maybe more. So let's take a look over here. I'm pointing at this bend in the line on the far left side. How many hydrogens are attached to that carbon?
2.
2, because there's a carbon there and a carbon up. But there have to be 4 bonds. So remember, organic chemistry, we try to simplify to distill down to the easiest possible way to draw it. And that includes not showing all of the hydrogens that are connected to carbons.
I bet that'll be a pain.
If a hydrogen is attached to a nitrogen or an oxygen, we're going to show that. It is only carbon hydrogens that are implied. Otherwise, the system wouldn't work. It would be way too confusing. Okay? So could you count up how many hydrogens are in the structure?
Yeah.
You might want to draw out all the individual hydrogens. That might help. So if there are 4 bonds around this carbon, can I get a volunteer to describe how we would determine the molecular shape? A couple of the same hands. Can I get a new voice? Matthew.
Okay. Well, if there's a central carbon, and you know there's going to be 3 bonds within those. Because, well, one of them's double, 2 single bonds, and therefore it's going to be trigonal.
Okay, electron pair geometry or molecular shape or both?
Okay. Both.
Great. Both because there are no lone pairs. All right? I agree with you, Matthew. So trigonal planar is going to be the electron pair geometry and the molecular shape. So I want you to think about the process he just described. So 1, we have to identify, are there any atoms that aren't shown that are implied? Once we know that, we can say, well, what's the steric number? What's the AXE? Because some of those steric groups might be lone pairs, and that's going to be important in determining the electron pair geometry and molecular shape. Then we determine the electron pair geometry, and finally we determine the molecular shape. All right? Those are the steps that we need to go through every time we're looking at a particular point on a molecule like this. You want to try another one?
Yes.
Okay, we're going to do another one. Due to popular demand. All right, go through the same process with the oxygen that has the arrow pointing at it. Try to do this for as many as you can. Bonds to oxygen. And how many lone pairs do you have? So think about that. Think about the trends we start to see in each different group, and then use that to start being a little bit. It'll speed up how you can respond to these. All right, a couple more seconds. So can I hear from a new voice? I'm going to ask one question first, and then I want to hear from Kevin about how he answered this question. How many hydrogens are bonded to that oxygen that are implied that are not shown? 0. Carbon has 4 bonds, always. Oxygen, everyone else, if we have a hydrogen attached, we're going to show it. So let's not make those rules where we confuse hydrogens implied to other atoms. It is only carbon. Okay? Kevin, how did you decide what the molecular shape is around that oxygen? What's the process?
Well, there's 2 bonding domains, and then since oxygen is in group 6, it needs 6 electrons to get the word, but so the molecular shape doesn't account for the electron pairs, so you only look at the 2 bonds with the big shape.
Okay, so I would caution the terminology there. So the molecular shape does only describe where the atoms are, but you have to consider if it has lone pairs or not. If we only say, well, it has 2 bonding domains, it's going to be linear.
Yeah.
And so it's not linear. Why? Sir?
Because it has 2 lone pairs.
How do you know it has 2 lone pairs?
Because carbon needs 6 electrons to be stable.
Oxygen needs... So oxygen, you said carbon.
Oh, that's oxygen.
Y'all confusing me. I don't know.
Okay, so oxygen is in group 6. That means to have no formal charge, which there is no formal charge drawn on here. It is implied that there are lone pairs. It would have 6 valence electrons. 2 of those are shown here. In the bonds that it's sharing, that would mean 2 lone pairs exist there as well. So the more you do Lewis structures, the more you're going to remember these trends, that oxygen is very frequently going to have 2 bonds and 2 lone pairs. Nitrogen is going to have 3 bonds and 1 lone pair. We can kind of do this over and over. And so here we know that oxygen has 2 lone pairs. What's the steric number around that oxygen? 4, AX2, E2. And then we say, based on where the bonded atoms are in space, how do you describe that shape? Bent. So if we ignored the lone pairs, we would say it's linear. We don't ignore them. We then use the electron pair geometry to describe where the bonded atoms are in space because of the steric number of 4. Okay? Where do we end up with that? So bent is our description. You would not necessarily get that from just looking at that structure. This one happens to be drawn bent, but we might draw it in a way that looks linear, so we still have to go through that process. All right, let's do the nitrogen. At the bottom with the arrow pointing at it. Remember, go through the process, think about what's there that's implied, think about what the steric number, AXE, electron pair geometry, and then molecular shape. And yes, you're welcome to talk to the people around you.
Careful about with this is that this is more like a memorization tool, and I want you to be able to describe it based on how it looks. So, if you're up coming office hours, I could just spend 5 or 10 minutes showing you what I mean. That'd be really useful. All right, 15 more seconds. You will not be drawing these molecules on the test. You will be given a structure like this and be asked these sets of questions. Yes. All right. Can someone talk us through the process for this nitrogen? Can I get a hand raise and a new voice? Josh.
The nitrogen, it has a steric number of 4.
What?
3 bonding domains and 1 non-bonding.
Great. So how do you know that it has 1 non-bonding domain?
Nitrogen has 3 bonds and has 1 lone pair.
Great. So nitrogen is in group 5. That means we're typically going to find it with 3 bonding domains and 1 lone pair. It doesn't have a charge, so that's what we're going to find. And so it might be really useful as soon as you get a structure that you haven't seen before, go around and look for where all the lone pairs are going to be. What atoms typically have lone pairs on them? Oxygen typically has 2. Nitrogen typically has 1. And remember, that's true for everything in that group, right? What about group 7? Do they typically have lone pairs? 3. They typically have 3 lone pairs. So chlorine has 7 valence electrons. It only needs to share 1 in order to get iso electron to the nearest noble gas. That means it has 3 lone pairs. So that means that when I saw this molecule, I would automatically draw in 3 lone pairs around chlorine, 1 around each nitrogen, 2 around each oxygen. And that would help me think about these questions better. Can you finish describing, Josh, how you determine molecular shape?
Well, the answer is pyramidal, and just the lone pairs are going to be at the top, and the hydrogen 2 carbons are going to be coming off the bottom.
Okay, great. So you're visualizing what it actually looks like. So the one step you didn't describe that I think you're picturing is that you went from a steric number of 4, AXE would be yeah, we don't write the 1, right? So just AX3E, which means that it has an electron pair geometry of tetrahedral. Do we need the AXE or the steric number to determine electron pair geometry? We only need a steric number. We can also use the AXE, but we don't need that level of detail. Electron pair geometry is where are the domains, not each specific domain. So if I gave you a steric number and asked for molecular shape, you say, I can't do that. We can't answer that question because we don't know what's bonding and what's non-bonding. Okay? And then from there, I would say once we know it's tetrahedral electron pair geometry, we say, well, one of those is a lone pair. So we're going to describe the other 3. They're in a triangle shape, like a pyramid with the nitrogen at the center. Great. Very nice description. Do you think you could do this for any molecule I gave you? Yeah. Would you need to practice a bit?
Yeah.
Okay. So that's why I gave you the back sheet. We're actually not doing any of those in class. Those are all some practice molecules. What do you notice about at the very beside each molecule? You guys notice a dollar sign? What does that represent? What does the B stand for?
Billion.
Billion. I hope that's not how much it costs.
I mean, well,
That's how much they make up from it.
That's how much they made 2017.
and just.
That's like the GDP for a lot of small countries, right? Some of them are close to $10 billion that they make in 1 year. So if you're ever interested in talking about what drug discovery and development is and how those numbers relate to corporate greed versus betterment of humanity, I love having those conversations. My PhD is in medicinal chemistry, organic medicinal applications. So it's a lot more complicated than just looking at that number and being like, we're getting ripped off. True, we might be getting ripped off, but there's more to the story than just that. So I think we're going to, for the sake of time, we're going to keep rolling. So let's see if we can answer these questions. These are the questions that were on last class's worksheet. So if you want to see the wording of those, pull out Wednesday's worksheet. Couple more seconds. Closing out. All right, which is it? Is it the number of bonds and lone pairs or the number of electron domains? New voice. Ruby.
It's the number of electron domains,
Why?
because if C said the number of bonding domains and lone pairs, it would be correct, but it's the number of bonds.
Great. So in this statement right here, it's not the number of bonds. Remember that carbon that had a double bond and a single bond and another single bond? That was only 3 domains. So the number of bonds would have been 4 bonds around that carbon, but there were only 3 domains. So we need to make sure we're talking about how many lone pairs and how many bonding domains, which is a total steric number. All right, so whenever we're determining electron pair geometry, steric number is all we need. Can we do it from AXE as well?
Yes.
We can, because x plus e, the total number, gives us a steric number. But we don't need AXE to answer that. So then which is the best answer for this, for molecular shape? Couple more seconds. Trey, which one of these do you think is the best answer and why?
I think C, and just based on the simulation we were messing around with, and like the example you gave earlier, where if it weren't for like a lone pair, a structure that had those two domains would be linear instead of bent, so it's obviously a repellent.
Great. And I hope that everyone got the opportunity to use the simulation the way you're talking about. That if you took one of the atoms and moved it in the simulation, it didn't just rotate the structure. Hopefully what you got to see there is as you moved any domain of electrons, whether that was a bonded atom or a lone pair, you saw that the other bonded domains or non-bonded domains would get closer for a second. The bond angles would decrease, but then they would be repelled away until they found the maximum space that they could have. So if you haven't got the chance to do that, go back and grab the atom or the lone pair and move those, because if you just click in space, it just rotates. So there's real power to seeing that repulsion occur. So does the class agree with you? Most of the class agrees with you. It is the repulsion between those domains of electrons, lone pairs or bonding domains, that drives this. So then what do we use to determine the molecular shape? All right. We have a large number of people that are saying that that would be the AXE notation. Why could we not determine the molecular shape from the steric number alone? Love?
Because lone pair electrons, lone pair domains repel more than normal bonds.
Okay, so you're talking about theoretical versus actual bond angle, and that's true, but that's not why we can't determine the molecular shape. Kevin?
We don't know how many bonding domains versus
Great, so this is a good example here, AX2E2. What's the molecular shape of this one? Molecular shape? This is bent, but if we only said steric number 4, you'd say it's tetrahedral. But that doesn't describe where those two bonding domains are based off of the lone pairs. So we need to know with specific detail how many bonding domains there are and how many non-bonding domains there are. We can't answer molecular shape unless we know AXE. So then there are examples like we just talked about where compounds have the same molecular geometry and electron pair geometry. When is it when we have a difference between electron pair geometry and molecular shape? Talk to your neighbor for a second. What generates a difference between molecular shape and electron pair geometry? Lauren, what did you guys answer? Say again? So if there's the lone pairs, then what happens? Okay, so it's not only about more space, we're just talking about electron pair geometry versus molecular shape. So if we have a lone pair, then super chemistry dad joke. Then we have, well, probably this kind of lone pair. We end up with a different configuration between electron pair geometry and molecular shape because we're describing where the atoms are. So if one of our domains is not an atom, not a bonding domain, then that makes a difference. And then the second part of, I think, what both you and Kevin were getting at is that the actual bond angle will change slightly based on the electron density of a lone pair, double bond, or triple bond as well. Okay.
It's really not due to pairs.
So, just to summarize, Vesper is all about valence shell, right? We're talking about what group number it's in, where those electrons end up. Electron pair repulsion. So, if you just keep that in mind about the repulsion, the simulation hopefully will help you get there. We can determine electron pair geometry from that. From that, we can determine the molecular shape. This is a slide for summary. You can go back to it if you want. But we have to draw the appropriate Lewis structure in order to answer all those things. So as I mentioned earlier, on an exam, you would have to be able to determine steric number, AXE, electron pair geometry, molecular shape, and hybridization, which is what we'll be talking about on Monday. When's our next exam? October 8th, a week from Monday. All right. I got questions about how soon I can get you back your exam wrappers. I don't know. It'll take me a little while to go through those. So I'll try to get them back as soon as I can. I will absolutely try to have it done before the next exam so you know how you stand going into it. But the most important thing is that you kept up and you have worked on those questions, and the grades will be filled in when I get the chance to. So be patient with me, please. The next thing we're going to talk about is there a net dipole around any one of those atoms or in the entire molecule? So let's talk a little bit about that. And then the last thing is, based off of the net dipole, if we had this molecule and one that had an oxygen here instead, you guys would have to tell me which one is more water soluble, which is important for druggability and a whole bunch of other properties of the molecule. We're also going to talk about the number of pi and sigma bonds, which is shorthand double and single bonds in a molecule, which means you have to draw in all the hydrogens and think about that. All right, let's talk about drugs.
Oh, it's good.
This is a question on your worksheet, maybe on the number 2. What do you guys think about generic drugs? Couple more seconds. So when you go to your doctor, sometimes for the sake of cost, they'll describe you a generic drug. It's really important that we know what it is we're putting in our body. So if I have a sore shoulder, I'll take some ibuprofen for my sore shoulder. Ibuprofen's name brand is Advil. Am I getting the exact same thing when I buy Advil and when I buy the Walmart brand? Yeah. The answer is no. It's not exactly the same thing because the company that makes Advil puts a sugar coating on it and the generic doesn't. That's the difference. Okay, there's also Advil PM or Advil extended release. That means that all of the things that call themselves ibuprofen have to be the exact same chemical formula, but then they package it in something. And the extended release stays in your stomach for 12 hours and it releases over a longer period of time. So the formulation of it, the way that it's packaged, and the way that it releases into our body can be different from a generic versus a non-generic. I have some friends of mine who are pharmaceutical sales reps who do not have any background in science whatsoever, and they literally tell their doctors they're working with that, sometimes generics are found, they have like glass in them and stuff, and like they're different compounds. What? You should not be allowed to talk to anybody, let alone a doctor. So hopefully the doctors push them out the door. I would never buy anything they're selling, whatever it is, because they sell at all costs. Okay, so what I want us thinking about is what we have on the back of this page is a whole bunch of different pharmaceutical drugs. Some of those, all those three on the back are on patent. The one on the front is not in patent anymore. That means that anyone can make a non-patented drug, a drug off patent. So that's why I didn't put the Abilify sales in 2017, because it is no longer on patent. And so anyone who wants to can make it. It's public information, what the structure is. And as long as they make it and get approval that their process is clean by the FDA, then they can sell that drug. So here is Taxol, a very effective chemotherapeutic drug. And what I want to start to think about is there's a lot going on in these molecules, right?
Yeah.
What does this dashed bond mean?
It goes back.
Going back into the paper, so there's a hydrogen that's not being shown that's coming out of the plane that's tetrahedral electron pair geometry and molecular shape. I want you looking at all this, and I want you thinking about what are regions where there's higher electron density and lower electron density. Because this molecule doesn't just go and magically work in the body. This drug goes into the body, interacts with proteins, which are these ribbons that are also individual atoms and bonds. But because there's high electron density and low electron density in certain areas, it fits and interacts with a specific part of our body that only that drug interacts with. And that means it has the physiological effect that we want. So we need to be thinking about how it is that those drugs interact with water and other polar and nonpolar groups. We don't have any time, so we can catch up after class if you want to chat about it. The last thing,
do proteins like that?
There's good reasons. So the last thing we're going to talk about is the scale of electronegativity. We had mentioned this in class in the last few days. So electronegativity is defined right here. The relative ability of an atom to attract electrons to itself in a bond. So what I want us thinking about, what trends do you see in the periodic table? What are the most electronegative atoms on the periodic table?
Fluorine.
Fluorine. Think about the atomic radius, and think about how close it is to noble gas configuration. On the far left side here, we have the ones with really low electronegativity. So when we pair things together on the opposite sides, those electrons are not only not going to be shared very evenly, they're actually going to be split. One is going to pull the electron away from the other. So what I want you thinking about, and maybe this is good for you to fill in before class on Monday. There is a homework this weekend. I don't think it's extremely long. It's a lot of stuff we worked on. Is I want you to take this list of bonded atoms, and on the next page of your handout, you'll see that there's a number line. I want you taking all 7 or so of those bonded pairs, and I want you writing what's the difference in electronegativity values for those two when they're bonded together. So let's do one together. We have carbon bonded to carbon. What's the difference in the electronegativity values? So I would then write carbon, carbon right here, and that's at 0. Let's do one more. Let's do carbon to hydrogen. What's the difference between those?
Not very much, but it's higher than 0.
So you have the values on your table.
0.4. We don't have hydrogen.
Hydrogen isn't listed? So hydrogen is 2.1. So you might want to add that to your table if you don't have it. Hydrogen is 2.1. Sorry about that. That's bizarre. I'll also post these slides so you can look at this diagram if you'd like. I thought the values were all the same, but I didn't realize the hydrogen was missing. So where are we going to put C to H bonded? 0.4 difference. So we could write... Okay, and I want you to fill in the rest of those bonds here. And I want you thinking about some trends that you might see. You might also try doing a couple other pairings across the periodic table. And we're going to start thinking about naming of everything else as well. All right, hope you guys have a good weekend. Don't forget the homework is due Sunday. It'll involve electronegativity a little bit, I believe. Post questions to campus discussions if you have any questions.